Welcome to Brain Vision.
Hello everyone, this is going to be the solution to problem 48, chapter 24 of calculus physics. We are presented with a scenario where we have four polarizers in a row, and we're taking them out one by one and seeing what the emergent intensity on the far right of all the polarizers is going to be. So first scenario, we would normally have a vertical polarizer here, but that's what we've removed. So removing that, we have vertically polarized right coming in. And so let me just write what the end polarization is going to be, or what the end intensity is going to be. It's going to be the initial intensity times. So this is a cross section of what's happening here. We have a polarized light at the vertical direction that is making an angle 30 degrees with the direction of the polarization going out with the polarization axis of the polarizer. So projecting this polarization onto the polarization axis through the angle 30 degrees, we get that this is going to reduce our intensity by cos squared of 30 degrees. Moving on to the second part, we have this intensity coming onto the second polarizer, and this has a polarization axis that is horizontal. Now, we have been polarized 30 degrees with respect to the vertical direction, which means that our current polarization is making a 60-degree angle with the horizontal. And so we need to project through this angle onto the polarization axis, which means that we're going to pick up another factor of cos squared 60 degrees this time. And so this is the resultant intensity that's coming on to the third and last polarizer, where we see that we had been polarized horizontally, and this new polarization axis makes an angle of 60 degrees with the vertical, which means that this angle is 60 degrees. This angle here is 60 degrees. So that means that our current polarization is going to be making a 30-degree angle with the new polarization axis. And so we're going to pick up another factor of cos squared of 30 degrees. And so this is going to be the resultant intensity coming out of far right. And for an incident intensity of 27 watts per meter squared, this is going to work to be 3.8 watts per meter squared. So that's the answer to the first part. Second part, imagine that we had kept the vertical polarizer, but we had removed the 30-degree polarizer, which means that the next polarizer after the vertical one is going to be horizontal. So this means that our the light polarized that parallel to the vertical axis is going to come on to the polarizer that has a polarization axis that is horizontal. And so since these two make a 90-degree angle with each other, we know that there is no light that is making through its way the second polarizer. So the resultant intensity is going to be 0 watts per meters squared. So that's the answer to the second part. The third part, let's say that we had removed the horizontal polarizer, which is the third one in this line of polarizers. And in this case, we have a vertically polarized right that comes in and it happily makes all its way through the first polarizer. Then it comes across the second one. Now, as it goes through the second one, it's going to be polarized at 30 degrees counterclockwise to the horizontal direction, which means that when it comes onto this new polarization axis that is rotated 60 degrees clockwise with respect to the vertical, it's actually going to be making a 90-degree angle with the current polarization. And so again, the resultant intensity is going to be 0 watts per meter squared. So that's the answer to the third part. And lastly, if we remove the very last lens, that is the 60-degree clockwise rotated polarization Polaroid, then in the first part, we have a vertical polarizer. And so since we have incident vertically polarized light, all of the light intensity makes its way through. So here, it's still S bar 0. Now, I'm going to write again the final intensity over here. So we have S bar 0 so far. S bar came in, and all of it went through the polarizer. Now, as it comes onto the second one, the polarization axis is rotated 30 degrees with respect to the vertical or the current polarization. And so we reduce the intensity of cos squared 30 degrees, and we move our way through to the third one, or the last polarizer, which is rotated at, which is actually horizontal, which means that with respect to our current 30-degree rotated polarization, this new polarization axis makes a 60-degree angle. And so we're going to rotate through this angle using cosine squared. And so we reduce the intensity further by cos squared 60 degrees. And this way, we end up with 5.1 watts per meters squared. And so this is our